Hello guys, welcome back to the ANSYS CFX course series. This is the second part of our tutorial number 2, in which we were talking about that how we can run the parametric study and can do the design optimization using ANSYS CFX along with the other ANSYS tools. So in the last part we have set one input parameter, which was the called inlet diameter, and two output parameters that we want to see. And you can see here it provides us the results against all of the diameters. So now what else we can do? We can also use more than one number of input parameters. Like let me open the setup again, and let me go to the expression and right click on expression, and you can see it here. I can use it as input parameter. Okay, now also I am going to change the inlet as the expression input. Okay, so no, let me make it constant 1500. Click on OK. Now we have to update the solution and results. So you can see that the software did not initialize the work from the start. So what we have to do to avoid this, first of all, stop the solution and click on yes. Come to the setup, and solver control. So first of all, change the minimum iterations to 10, because in some cases when the solution is converged but the boundary conditions are changed, the software did not get that and take it as converged solution. So we will not get the exact results. So to avoid that, set the minimum iteration to 5 or 10. Click on OK, close the window, come to the solution tab, define run. Instead of current solution data, click on initial conditions and start run. So wait for the completion of the solution run. So then we will do the next step. Okay, the solution is completed. Click on OK, come back to the workbench tab and go to the parameter set. So now you can see we have two input parameters. I can change the overflow to like 1700. $1600, 1750, 50. Let's say 1400. Okay. So just click on update all design points and wait for the solution to be completed. Okay guys, so you can see all of the parameters are being calculated by the software, and you can see the output here. So if we see the minimum difference in the outlet temperature between the maximum and minimum value that we find here, and also the temperature is not minimum, but it is showing that the temperature at the outlet is evenly distributed, so the mixing goes well. So we can see that the temperature is high at 1700, and the difference in the minimum and maximum value of temperature at the outlet is also minimum at this dp2. dp is stand for design point. So even with the higher mixing rate, the temperature at the outlet is down. So now you can see that how the parametric study can help us to optimize our design. So let's see the other optimization tools in the workbench. Okay, in the design exploration, we have to choose the response surface. So we will get the design of experiment tab. Click on edit. Okay, you can see here we have the input parameters and the output parameters. We cannot edit the output parameters, but we can edit the input parameters, like we can control the diameter of the cold inlet from, let's say, 15 centimeter to 30 centimeters, and the flow from 1200 to 1800. Okay, so number of retries I'm going to edit to, but let it be 0 for this case. Click on any and all done. Okay, just click on update now and wait to for the software to be finished the studies. He have taken the 10 points as default function. So the software will calculate the data on all of these 10 points and give us the results. So wait for the software to calculate the desired points. So the analysis is completed. So we can see the temperature at different points, and if we see this, we got the minimum temperature like about approximately 300 Kelvin, and also the difference is minimum at this 30 centimeter diameter with 1500 kilogram per second flow rate. So now come back to project and click on the response surface. Click on update. So you can see the different types, like you can see the chart of diameter versus the outlet temperature. You can convert it to 3D too. So you can see the response, the outlet temperature versus the inlet diameter, and also the flow rate. Also the y-axis difference in temperature. If we see, we can see the local sensitivity, and this is the curve graph. Also we have gathered the best point. So you can see the prediction depending upon the observed points, and we can use this data to optimize our system design. So now let's come to the project again. So we can see the direct optimization, or now we are going to use the response surface optimization here. So click on the optimization. Now let we set the lower bound and upper bound, and in the objective we have to create the objective on the hot flow to minimize the temperature. I am using just a single objective here, and all done. The constraints are defined, like the lower bound and upper bound, and for the diameter also the lower bound and upper bound is defined. Just we have to click on update button. So it's have done. So you can see there he have chosen some of the points. But he did not optimize the value. So let me go to optimization again. Change it to so let's add another objective. Let me delete these objectives and let we insert and delete it from here. No, we cannot use the input parameter. So now the design is optimized a lot, like you can see. It has minimized the temperature to 300 with the hot flow to 1200 and chord inlet as 20 diameter is 23 point, approximately 24 centimeter. So this is better. There is an error. There is a conflict between the objective and for one of the we are not getting the exact points due to the rough mesh size. So now we have selected one of the more point, like about 300 Kelvin at the flow rate of about 1500 kilogram per second. So by choosing some of the different points, we can get the optimized design. So that's all for today. I will see you in the next class.